Hello and welcome back to another LeetCode problem. This time we're looking at trapping rainwater number 2, which is LeetCode 407. It's another hard problem. And if you've seen the previous video, that's where we dealt with the first version of that problem, where we had a one-dimensional height map. Now we're dealing with a two-dimensional height map. But I'm getting ahead of myself, so let's just read through the problem description to see what we need to do. So we're given an m by n integer matrix height map representing the height of each unit cell in a 2D elevation map. Return the volume of water it can trap after raining. And this is how that might look like. Let's just look at the constraints real quick before we dive into the examples. So m is the dimension is m by n, and it's guaranteed that we have at least one cell in our height map. We also have an upper bound, but of course we don't care for that for our runtime complexity analysis. Otherwise, everything would be constant space and constant time. And the values of the heights are between 0 and some positive number. And that's kind of what it looks like. So, yeah. So from these examples, it seems pretty obvious what we need to do, right? We have a range of blocks, and we can trap rainwater only when the surrounding blocks are, if there is like a sink or a valley between those blocks. Otherwise, here at the edge, it can't be trapped because it will just flow off into the nether realm. Anyways, so let's see. Now, how can we approach this? In the version 1 of this problem, we were able to just iterate through the array, and we would mark, for example, this block as a potentially trapped rainwater. And it was quite easy because we only had to check, okay, what is the next peak as we iterate through the array? You know, is the water trapped between the previous peak here and the next peak? And then we would add that to our result, the total amount of trapped rainwater. Now in 2 dimensions, it becomes a little bit more complex because now it doesn't just depend on the next peak of whether we can trap the rainwater. It depends on all of the neighbors around that area, right? If one of the neighbors was removed, if the height wasn't here, we wouldn't be able to trap as much rainwater in here, or any at all. Right? If we remove these 3 blocks, then we couldn't trap any rainwater in here. So how can we deal with that? Well, the challenge of this problem is really to figure out how do you check, if there is an area that can actually trap any rainwater. And one way you might approach this is by just, well, you could start, for example, with all the blocks that are on the side of your height map. So all of the edges, because we know that outside the edges, the height will be 0 and nothing can be trapped in there, since all the other heights are also 0 or larger, but not negative. So if we kept track of all the blocks that are on the boundary, and then we pick the smallest block, right? And we pick the smallest block from the boundary to see if there is a next block, if it has a neighboring block that is maybe lower, then this guarantees that there's going to be trapped water there. Because we already have the boundary, and we know that all the other blocks in the boundary that are larger than our current block. So if the neighbor of a block on the boundary is smaller than that boundary block, we know guaranteed that there's trapped water in there. So we could actually iterate. We would add that block to our boundary. We would add the amount, the height difference between the boundary block and the neighbor of the boundary block to our amount of trapped water. And we would then pretend that this block is this new block, this neighboring block, is now a solid block that is now part of the new boundary. And that way we could start to propagate through all of the neighbors of the boundary and check, if, well, we will add them to the boundary, and we'll also collect potentially trapped rainwater. And this is guaranteed to work simply because of the fact that we always pick the smallest element on the boundary where we know that it might enclose trapped rainwater. So what do we need for that? Well, the first thing we will need is add all of these boundary blocks to our boundary. So we need to have a data structure to keep track of the boundary. But we also need a data structure that allows us to pick the minimum element from the boundary. So obviously, a heap would be the first choice for that, I suppose, so that we can pick out the minimum element at any point in time. We also need to keep track of elements that we've already visited, because we don't want to revisit them again. Otherwise, we're going to run into infinite loops. And we need also, the result variable. So in total, we're going to need, if we say m times n is our total number of elements, we're going to need a heap that will contain that many elements in the worst case. So that means the operations will be k log k, where k is equals to m times n. And we're also going to need a k space. So that's the approach that I would try to implement. I have not tried that before, but let's do it. N by m log n by m time and over m by n space. Right. So I've not tried this implementation before, so this will be my first time doing it. Let's see. So we're going to need a heap queue. So from heap queue import heap push, because we're going to need to add neighbors to the heap queue as we progress. We're going to need heap pop to be able to remove the minimum element. And we're going to use a heap phi just to make it possible in the beginning to initialize the heap queue in linear time. So that is one thing we need. Let's see here. So we're going to say our min heap. Our heap is just an array, but we need to initialize it, right? So let's see. What did they say? So m is the height of the height map, and n is the width of the height map. Height map at the first row, yeah. So there you go. Now we have to add all of these elements to it. So, but we also have to put the coordinates in it, right? So that we know which element to access when we try to retrieve its height. And the way we do that is, well, we just iterate we need to iterate over the first and last row and the first and last column in our height map. That will form the boundary. So and I'm going to use x and y. Actually, I don't like m and n. I'm just going to use, this is the height and n is the width. Just going to use that as my variable names. That makes it a little easier to know which one should be x and which one should be y. So for x in a range width, and now we need to pick the first how do you say, column. No, I'm sorry. We need to pick the first row and the last row. So for y in range, well, let's see, in 0 and height -1. So yeah, and then the height is at that position is height map at y and x. So well, So we need to put that into our heap. And we're just going to be doing heap append. Now we put the height first because that's what the heap is going to be ordered by. And then we're just going to X and Y, add X and Y as well. Right. So that's the first thing. And now we need to do the same with the first column and last column. So for X in column 0 and the last column. And for Y in, well, range height, right? What you would think. But we've already added the corner elements in the first loop. So we have to start actually from -1. Cool. Yes, so that's what we need to do so that we don't add the corner elements twice, right? If we add this column, and then we pick this row and this row, we've picked the 4 corners twice. So we want to avoid that. And this is how we avoid that for the rows, but we also have to, let me think. Yeah, I think we should be good, right? Or am I overlooking something here? Because we need to add them once, these corner elements, which is what we do here. But then we need to skip the corner elements here. Yeah. Zero and 1. Yes, I think that should be correct. Okay, cool. So now we do the heapify. Heapify, and this is also interesting to know. Heapify is a linear time algorithm. So even though we are creating a heap, it's in linear time. But if we were to create this with heap push, it would be basically k log k time. Well, I mean, height plus width time, because this is O of height plus width, so m plus m. So now we've created our little, I guess, min heap that allows us to pull out the minimum element and from the boundary. And maybe we should call it boundary actually, right? Yeah, maybe that's a good idea. We call this boundary. Now we need a data structure to remember elements that we've already visited. And we're just going to use a set in this case. And we're going to put x, y tuples in here. And that allows us to quickly check. Or we could just put these elements as well if we wanted to. Yes. So now what to do? Well, while we have any elements that we need to process. So we're going to use this as our processing queue, the boundary. And we're going to get the min. Well, we get an element out that is heap pop boundary. So this is now guaranteed to be the minimum height element, or if they're multiple, it's going to be one of them that is on the boundary, and none of the other boundary elements are smaller. I forgot we also need to store our results somewhere. Yeah, result 0 to put this here. Maybe I'll put this on top. Maybe we'll just put it here. And result is going to be our trapped rainwater. Cool. So what do we do now? Well, we need to get the neighbors, right? So for getting the neighbors, maybe we should have a little helper function so that we can, when we get the neighbors, we want to get neighbors that are only the same height or that have not been visited. And do we care about them on the boundary? Yeah, that's maybe something to consider. If a neighbor is on the boundary, do we want to go there? I don't think we want to go there in that case. So let's keep that out. Maybe we need to have a data structure that tells us, if an element is in the boundary list or not. That's going to be a case to handle. Anyways, for now, we're going to say, okay, what are the neighbors? So for neighbor in get neighbors of our current element. So, and our current element is, well, it has a height, current height, and we're going to get the X and Y positions from it, right? And we're just going to get the current neighbors of X and Y. And we might as well pass in the height as well. We could look it up. Or maybe we shouldn't pass it in. Maybe we should keep it simple. So, like so. And for that, we're going to need a little helper function, def get neighbors of X and Y. And so we're going to need to get the height for that element if we don't pass it in. Height map to position by X. And now we need to iterate over all of the potential neighbors. And we're not looking for diagonal neighbors. We're only looking for direct left, right, up, down neighbors. As you can see here, the diagonal is not interesting. Well, it doesn't matter, right? For trapping the rainwater, that's what I mean. Cool. So for, well, we need to have like we need to compute like X minus 1, Y plus 1, and all this. And we can do it like this in zip. So we're going to have 2 offsets for the X and the Y position. And then we just compute the X and Y position of those points. That would be dx plus x and dy plus y. Then we have to perform a couple other checks here. Neighbors. And we're going to return in neighbors array at the end. So let's fill out these zips. So at the first, we want to return the element to the left. So dx will be -1, but y will be 0. Then let's look at the element above it. The dx will be 0 and dy will be -1. Next, we're looking at the element to the right of it. So dx will be 1, but dy will be 0. And finally, we're looking for the element below. The dx will be 0 and dy will be 1. That's an easy way to iterate through that. And now we need to make sure that we're actually in bounds of our height map. Otherwise, it's an invalid position. If dx smaller than 0 or dx larger, well, no, sorry, px smaller than 0 or px larger or equal than width, that means we can't do anything with this. We're going to skip this position as a potential neighbor. Continue. And the same for the height. Py smaller than 0 and py larger or equal than the height. That's not going to be a valid position. Height. Right. So now we're going to do that. Now what we need to do, we need to get, well, we need to filter the neighbors based on that they have at least the height of the block at position xy. So if height map at position py px is larger, well, no, if it's smaller than our height map at that position, we're also not going to consider it. And otherwise, only otherwise, we're going to add this to our neighbors. And yeah, and we might as well just return the height like so. We're just going to say h equals that. And then we just pass in this as the next, well, one of the neighbors that is smaller or equal to the height of our current position. Now, what we don't have here is checking of whether it exists in our visited, right? So what we have to do if neighbor and visited, we're going to ignore it, right? And just thinking, what should we do with this? Well, I'm thinking, you know, we could use this as just basically just a position or the coordinates, because right now what we're doing is we're returning elements from the heap, but in the heap we're storing arrays, right? So now we're actually assigning the array values to individual variables. So then we pass in back and forth individual variables, and now we're checking if neighbors and visited, which just means we'd actually have to construct and well, not to construct, but in our neighbors we're also dealing with an array of values. So maybe we should simplify that real quick. So this would be maybe a position or chords, or this could be a cell, you know, and maybe just say, okay, let's get the neighbors of that cell. Right, and then what we pass in here is basically the cell, and then we can say, well, that is the height, the x and the y is the cell. So, and we should probably call this pH for the point height, like so. If pH is smaller than height, then we're going to continue. Alexa, stop. Sorry about that. Yes. Yeah, so now I think that's a little bit cleaner. I think that's a little bit cleaner, yeah. Let's do it like this. So we have a cell, we pop that out of our boundary, then we get the neighbors of the cell. If the cell is already visited, we're going to continue. And by the way, when we pop a cell out of the boundary box, we should add it to visited as well, so that we don't revisit it at any point later. And if cell in visited, we also can continue in case we add a cell multiple times. In case we want to visit a cell multiple times. All right. So that's kind of the first part. No, sorry, the first part was computing the hash map. Then we're going to, computing the boundary, which is going to be our min heap. And maybe we should put that into a little helper method as well. Build boundary heap. And we just do that like so. And then we return it. So all we do now is build boundary heap. And yes, so now it's time to think again. So we have built our boundary. Now what we want to do is we want to check, well, we pop the minimum element from it out. And when we do that, we're going to check out all of its neighbors. If the neighbors are already visited, we're just going to skip them. But if they are not visited, that means there's potentially trapped rainwater there. And so the trapped rainwater is basically the difference in height of our cell right? So that would be cell at, remember, 0 is the height, and it's minus the height of the neighbor, because we know the height of the neighbor is smaller than what is in the boundary, right? That's what we know. Now, what do we do in case that the neighbor is larger? Well, in that case, we are not going to trap any rainwater, but we still should add it to our boundary. So actually, filtering here is not a good idea. So we should probably ignore the filtering and return all the neighbors. But what we should do is we should have the case distinction right here. So if the height of the current cell is smaller or equal to the neighbor, well, we're not going to trap any rainwater, are we? That's only in the other case. That's when we do that. And in that case, we can say we are adding this because it's guaranteed trapped rainwater, as I explained earlier. We can add this to our result. Now, for this case, what we have to do is we still have to add this new neighbor cell to our boundary. And so what we'll do is we do a heap push boundary neighbor. And now it might be that we have a neighbor. For example, if we pull out, if for some reason we were to process this node right here, a larger neighbor would be that node here, that cell. So it might be that we're adding a cell twice to the boundary, but that's okay, because once we process one of those cells from the boundary, we'll mark it as visited, and when we pull out the cell for the second time, it will already be in visited and we'll just skip over it, right? So adding it multiple times doesn't really matter much. Cool. So yes. Yes. Keeping track of what cells are on the boundary to not add them. That would be, I guess, an optimization, but we don't need it, I think, to get the code to work. Cool. So yes. Now, if we have identified that the neighboring cell is smaller, then it's guaranteed to be not on the boundary, right? But we also have to add it to the boundary, but we have to add it with a new height, because now we have trapped rainwater, so that we know when we go from this node to a new neighbor, you know, we must assume that the height of this node is the height of its previous boundary cell. So what we'll add to the heap. Oh, and now I see that we might be making it a little bit difficult for us. So what we have to do now is we basically have to say neighbor height equals the cell height. But now we have a small problem, because if we put in our visited the coordinates including a height, you know, we might have a neighboring cell with its original height in there, and maybe then later the same position but with a different height. So when we put things into visited, we actually can't do it with with the height. So if we want to add something to visited, we have to add it from without the height, right? So we do this. And when we check here, we also have to check from from the second index on. Otherwise, it's not going to work. Right, so we've added water the cell gets added to the boundary, and that has already been added to visited, so that's fine. Let me think. If the height is larger, then we're just simply going to add it. Push height, yes. I think that should be most of it. Return result. Cool. So walking through an example is kind of cumbersome. We would probably need like a very simple example. Well, we want to test two cases. One where we have maybe a 3x3 height map where we can trap rainwater in the middle. We could try that. Now, I don't expect you to follow me when I start to explain this. This is going to take a long time. And I'll be saying this, that, then all the time. So maybe we should just try if this works, just to make this a little shorter. So I'm pretty sure that the logic should work. I'm just going to be faithful and try it out. And of course, we're running into our syntax errors because we didn't do the checking. That is to be expected. So now we have a problem because we can't just use the list. So what I'll do instead is I'll remove the height completely from, I can't do that, right? So what we do is we get the cell, and then we just extract the position on that cell, cell at 0, 1. Right. Otherwise, we're going to add the position. So we actually have to have tuples here, not lists. On hashable type list, that's why. So we have to put in something different than a list. So that's the position. And the same we have to do here. We have to actually check the tuples. Neighbor at position 1 is the X and 2 is the Y. Neighbor position, do it like this. Then continue. You push. Okay. Does it change anything? Okay, position, position, position. Let's try again. And we're getting the wrong answer, which is not great. So what on earth could be the problem? Well, now the debugging starts. I don't know if you can see what the error is. Why are we putting out such a large number? Results equals cell 0 minus the neighboring cell. Neighbor 0 equals cell 0. So we put out 24 instead of 4. If a neighbor position is invisited, we're going to ignore it. That makes sense. The neighboring cells, do we get the height correctly? Yes. We're getting the height correctly. Do we compute the neighbors correctly? -1 + 1, -1 + 1. I think so. And maybe we just get the position at this point. So neighboring, get neighbor's position. Let me see, think. So I was so convinced that this would work, but it doesn't. Okay, so debugging time. When we build our heap, so one thing we could do is we could print the heap first. So we're running into this example here, right? Or is it the problem maybe the minimum neighbors? Because, yeah, I think that might be the problem, because if we look at this cell, this is probably going to be the first one that we pull out of our boundary heap. And when we get the neighbors, we're only getting these two. We're not getting the ones at the here that are 0. So actually, it does matter of whether the neighbor that we pull out is on the boundary or not. If it's on the boundary, we can't use it to compute how much water we trap, because here it immediately would compute, oh, we have 2 units of trapped water here. I think that is the problem. So maybe we have to add tracking of what is currently in the boundary cells. So if we just put that in there as set. Now when we build the boundary heap, we also have to, build up the boundary cells. So let's move that to here. Boundary heap, boundary cells, going to be a set, and we're going to add this boundary cells at the XY tuples, and then we return the boundary and the boundary cells here. So, right, so now we have a hash map for that. And if a neighbor is unvisited, we're going to ignore it. If a neighbor position in boundary cells, we're going to ignore it as well. Whenever we add something to the boundary neighbors, we also have to add it to the boundary cells. Right, so I'm just thinking, yes. Are we maybe blocking the traversal then through the height map? I don't think so, right? If we, just because we can't go to a boundary cell, doesn't mean we can't go to a non-boundary cell. And if a cell is surrounded by boundary cells, well, that means that none of them are small on height, so we can ignore them. So now we're getting 2 instead of 4. So I think we've improved the code in the right direction, but we're not quite there yet. So what could be the next thing? What could be the next thing? Well, I'm going to make another small modification to the code while this process is in the back of my head. I'm going to add to heap. I'm going to add to the heap. I'm going to add the height and the XY position. And the XY position append. So this is going to be the position or the chords. Yeah, maybe let's stick with position, and then we just add the position here. Right, position here, same thing. Right, and when we pull elements out, all we do is, this should also be a tuple. We put in a position. Now we're pulling out the height and the position. And then what we do is for the neighbor, we can say the neighboring height and the neighboring position are basically the neighbor. Or we just iterate over them like so. If next position or neighboring position visited, we're going to ignore it. If it's in a boundary cell, we're also going to ignore it. And otherwise, we're going to add this neighbor to our heap. Right. And the result is our height minus the neighboring height. Now what we need to do here is maybe, well, we could also just modify the height map. Maybe that's the smarter thing to do. We could say height map at position Y and X, Y, and position X, right, like so, is equal to the height of that cell. And now we just push the neighbor into our height map. And you can just put H and the neighboring position in there. And this is right. Do we need to remove elements from our boundary at all? I don't think we need to do that. From our boundary cell set. Excuse me. Oh, if the neighboring height is larger or equal than the height, then we push it. All right. So that seems to have fixed it. So I guess it was that part where we had to modify the height map, and it is because otherwise, if we don't modify the height map, we will get back a neighbor, and if we have already filled water into that neighbor, then it looks like we haven't. Right, so we're putting in the previous height, not the adjusted height. I think that was the bug. So yeah, so this is so we went through a couple of iterations here. Let's see if we can now pass the final test. All right, cool. So that works. Yeah, and it also explains why this is a hard problem. There's so many things to get wrong. So I guess, so what are the learnings? Well, one thing I want to would now try again, now that we've adjusted the height map, if we actually need the boundary cells. That's one thing that I would like to test. And we can very quickly check if we need that by removing this line. So let's test that. And it still works. Okay. Very nice. So what I said in the very beginning, that we probably don't need that, is correct. So we don't need that. An unnecessary fix. So we don't need the boundary cells. So let's just remove that. Boundary, and right? And I guess the learning from this is you actually have to update the map, the height map, as soon as you consume a cell that is not on the boundary and from which you get actually water, right? As soon as you do that, you need to adjust the height. And otherwise, the pattern is simply have a min heap that allows you to extract the minimum height element from the current boundary, and then you just advance the boundary. And there are always two cases. One case is that the neighboring element that is not on the boundary is either larger, in which case we cannot trap any water, but we're going to add this larger element to our boundary. And if it's larger than the other elements on the boundary list, it's not going to be picked for a while, right? We're always looking at the smallest element to see if, we can start to trap rainwater from that one, starting from that one. And the other case is, well, if we can trap water, we need to add this element to a boundary, but also adjust its height. So yeah, priority queue, in-place updating of the height map, and yeah, and then just basically traversing the 2D map. So yeah, thanks for staying until the end, and good luck trying this on your own.